speaker, Dr. Inez Fung, here tonight. But before I introduce her fully, I would just like to take a moment to thank the sponsors of this event. Specifically, the Carolina Climate Change Seminars are generously supported by the Office of the Chancellor, the Office of the Vice Chancellor and Provost, the College of the Arts and Sciences, and the Institute for the Environment. We especially thank Chancellor Carol Holt and Provost James Dean for their enthusiastic support of this event. We are so glad to be able to hold these seminars here at UNC Chapel Hill, as we are grateful for this opportunity to bring predominant and influential climate change scientists to better inform us all on their areas of speciality and on this global concern. We strongly believe that these talks and the conversations which follow are a vital part of making this science accessible. Our speaker tonight is Professor Inez Fung, a distinguished climate scientist from the University of California at Berkeley. Dr. Fung is a member of the National Academy of Sciences, the American Geophysical Union, and the American Association for the Advancement of Science. She's also a main contributor to the 2007 Intergovernmental Panel on Climate Change, which was awarded the Nobel Peace Prize. And her biography, Forecast Earth, is part of a series from the National Academy of Sciences aimed towards keeping middle school girls involved in the sciences. Tonight, though, Dr. Fung will be talking about carbon dioxide from space towards climate-free verification. After the talk, there will also be a short Q&A session, so please stick around. And after that, we'll have a reception in the atrium. We will probably have more food than we can eat, so please stay and eat some for us. Also, tomorrow at 12:30, Dr. Fung will be presenting a more technical talk on the climate impacts of deforestation, and that will be in the Tate Auditorium, and that talk will also be open to the public, so if you would like to join us for that as well. Without further ado, please join me in welcoming Dr. Fung to Chapel Hill.
It's really a pleasure for me to be here, and I thank you very much for the invitation. So I'm going to talk about CO2 from space, and I think one cannot talk about climate without talking about CO2, where the CO2 comes from and what happened, and where it goes and what do we do about it. So here is a picture of Mauna Loa. Up here, this totally changed. And so this is the Mauna Loa Observatory from Mauna Kea. So I just lost the figure here. And I don't know what happened, but anyhow, in front of it, you know, I don't need to show you the CO2 going up. Okay, since 1957, when the peeling went up to Mauna Loa, and so you can see the CO2 increasing as a function of time. My husband and I went there, and there was a sign that says follow the white line on the. So we followed it, and then there was a break, and then of course we disagreed about which way to go. Now we got lost somewhere in here. And that was when I can imagine when the peeling first went up in 1957, when there was nothing, and how the instruments were brought up there. On the other side, Mauna Kea is like sci-fi city. All the astronomers have their telescopes up there, and this is looking from Mauna Kea back to Mauna Loa. So before I go, I just say the units. CO2 now is close to, not yet, when the peeling started, it was in 1957, it was about 315 parts per million. That means if you go and grab 1 million molecules of air, you get 780,000 molecules of nitrogen, 210,000 molecules of oxygen, and 400 CO2. Okay? So here we have parts per million, and if I put into a petagram, and 1 petagram is 10 to the 15 grams, or 1 billion metric tons, then if it makes it all well in the atmosphere, it's about 1 ppm CO2. So what we're going to look at is scientific language. We use carbon on moles of CO2, but when we go into the policy realm, sometimes you see gigaton or kilogram of carbon dioxide. So the ratio, the molecular weight of 12 and 44. Okay, so I'll just go through this. So what I'm going to take you is on this life cycle of CO2. I think I have a love-hate relationship with CO2. I've been studying it for 30 years now. And I know all the little wrinkles here and there, but anyhow, so let's get moving. So obviously you know the terrestrial life photosynthesis here is a stomate. When the stomate opens, CO2 goes in, and that's the start of photosynthesis. But we have to, when we talk about CO2, it's the cycle. It's always a cycle. So there's the life cycle, there's the growth, mortality, and decay for ecosystems. So photosynthesis takes in about 120 petagrams carbon per year from the atmosphere. Plants breathe, so there's half of it goes back out. And then there's mortality, and then the microbes act on the detritus. And so there is about, or at equilibrium, there would be about 600 petagrams back up into the atmosphere. So the inventory carbon is about 800 petagram in the above ground vegetation and about 1200 in the soils. So you can figure out the CO2 comes in and hangs around for about 10 years. You know how long a tree lasts on average. And so then they die, and so they hang out in the soil. The much larger pool of carbon in the soil. So in the tropics, the turnover time, things decompose very quickly. So the turnover time of carbon in the soil may be 5 to 10 years. And I call those the fast spenders, whereas in the Arctic, those are the hoarders. Okay, so there's very little CO2 coming in, slow photosynthesis rate, but it's cold and the decomposition rate is long. So the turnover time of carbon in the high latitudes and the cold regions is about 100, 200, 300 years. Okay, and it's permafrost and large store of carbon there. So when we look at the difference between photosynthesis, and obviously this is a northern hemisphere perspective, you have growing season here in the summer, and then the decay season, the decomposition, is a longer season for decomposition. So then what the atmosphere feels is here, the photosynthesis is the net removal of CO2 from the atmosphere, and this is a net release of CO2 back to the atmosphere. You can see it very clearly in the Mauna Loa record. So it peaks, and you see the regular cycle. It peaks in May, and it bottoms out in October. So this is the photosynthesis and the decomposition, the net photosynthesis and the net release. And so we have this breathing of the biosphere, which is very evident in the Mauna Loa record. So you can also imagine this, that I have a seasonal imbalance, but if I have an annual imbalance, for example, if I have deforestation, okay, then I have no more trees, this goes to zero, but I would still have a lot of detritus on the ground. So there would be a source of CO2 to get. So it's always think about the CO2 in and the CO2 out, photosynthesis and respiration or decomposition, the microbial respiration and decomposition. So now we go to the ocean. So marine productivity, same thing. So we have this phytoplankton near the near surface where there's sunlight and there's nutrients, and then they get eaten as a food web. And so there's the detritus that falls down, and again the microbes decompose. And so if I look at the profile of dissolved de-ices, dissolved in organic carbon in the ocean, there's a depletion where there's photosynthesis, and then there's release or higher concentration where the microbes return the carbon back. So the cool thing about this is that there's 3 species of CO2, and the CO2 that the atmosphere cares about is about only 1 to 2% of the total. So you can imagine, this is really important, that the CO2 comes in, the chemistry immediately shoves it into the bicarbonate. Okay, so it hides it from the atmosphere. So this is the gas exchange. And this is why the ocean can take up a lot more carbon than, say, Freon or other inert gases. Okay, so there's nowhere to hide. Whatever comes in, there's a back pressure pushing things out. Okay, so The other thing to note is that if the biology changes, this profile changes. Okay? If there's more biology, this gets pushed this way. Okay, so more can come in, okay, from the atmosphere. Or if there's less biology, then there is less depletion near the surface, and that's where CO2 is tougher to get in. The gradient is smaller. So, so this is what I just said. Also, the other thing is lower pH. The chemistry is such that when the ocean becomes more acidic, you really think about, like at Harvard you would say champagne, okay? Okay, the lower CO2 at higher temperatures, your Coke fizzes out the champagne, the bubbles come out. So the solubility decreases with temperature. And at lower pH, the reaction goes back to CO2, so there's more gases coming out. And so if I have upwelling, I bring up cold water. If I bring up cold water, then I have higher CO2 here, and then the CO2 would be pushed out. Okay, so you always think about, again, cycle, but in the ocean, it's the biology which is doing that cycling of the photosynthesis and decomposition that sets up the profile. And that determines how much CO2 can go in. The other thing is CO2. The third thing is that the CO2 goes in. There's the ocean circulation in the North Atlantic where we have cold, salty water. The salty water sinks to about halfway down to 2 kilometers. And so then we have this great conveyor belt. The time scale is about 1,000, 2,000 years. And this was actually determined using C14, the decay, the radioactive decay as a clock. And so this is the ocean to hide the CO2 from the atmosphere, from the biology, which goes up, and the upwelling brings it up. You have to go down and ride this conveyor and hide from the atmosphere. Okay, you can go the long distance traveler here. So now we go to geology. And so what I just said to you is this biology on land, this growth, decay, respiration, but some of the carbon is not decomposed. And so in swampy areas, there's coal formation, and this was about the Carboniferous. You guys know where the Carboniferous is. Okay, 10 to the 6 years ago. Okay, here in the ocean, there's all that stuff going on, but whatever leaks down into the sediments, then after millions, hundreds of millions of years, high pressure and high temperature, then we have oil and gas. So the point here is that the oil and gas and coal are very old, okay? 10 to the 6, 10 to the 8 million years. Only 10 to the 6 years. So then you can look at the carbon cycle, the natural carbon cycle, where there's exchange between the atmosphere and the ocean, exchange between the atmosphere and the land. And then there's all this, the deep ocean, the ocean circulation bringing CO2 from here to there. And on top of it, there's the geologic carbon cycle. So what goes in the volcanoes erupt, and the CO2 comes out, very small amount. And so then the CO2 dissolves in the precipitation, in the rain, this chemical weathering of the rocks, and goes into the sediment, etc. So this is the many cycles that we're talking about. For my concern, I'm looking at the mobile cycle because I'm looking at 100 years, 200 years, and not 100 million years, okay, which is this one. So when we go to the atmosphere, obviously all of you know, CO2 is a greenhouse gas. Okay, for certain wavelengths, it can do this. Okay, so I asked the students, how did you know when we say CO2 absorbs energy, where does it go? Okay, so the CO2 gets into an excited, with a right wavelength, it goes into an excited state. This one is a weaker one, it can do that. Okay, so then the CO2 gets excited, and then it bumps into the nitrogen, it bumps into the oxygen. So that's how the atmosphere gets warmed. Okay, that's where the absorption is from the excited state And this is a natural greenhouse effect. And so when we perturb the carbon cycle by taking stuff from the 10 to the 6, 100 million year pool and now put it into the mobile pool, then we're perturbing the carbon cycle. So this is the graph I wanted to show before from 1957 or 55-ish to the present. So this is the Teeling's record from script, and this is the NOAA has taken over the regular measurement of CO2. So you can see the incredible rise, and this is high precision. It's 0.2 ppm, okay, accuracy. So in addition to Mauna Loa here, we have, the US has 4 continuous measurement sites, Point Barrow, Alaska, Mauna Loa, Samoa, American Samoa, and the South Pole, where there are people around all year round. And air is sucked in from the ceiling, and then it's dried, goes through cryogenically dried, so the water vapor is removed, and then the CO2 goes in with an infrared measurement. Okay, so those are very hard. Those are called in situ measurements, and those we have, I'm going to say, at least hourly data. Okay, continuous hourly data. But all the other sites, the cooperative sites here, okay, a flask is evacuated. Okay, so 2 of them, and so they are. And so if you are at one of these sites, you're told to go under clean air conditions, i.e. when the wind is blowing from the ocean or some clean air sector, you go out, you hold your breath, and you open the valve, okay, so the air rushes in, and you do 2 of them, so you do that, and so there's 3 sets, 1 set at the site, 1 set in transit, and 1 set for analysis in Boulder, Colorado, at the NOAA lab there, pre-analysis and lead lab. In addition to those, we now have other tall tower sites and aircraft measurements, and these are ships of opportunity when you can persuade somebody to do that on the ship, okay, wherever the ship is going. So it looks fine. We have a lot of measurements, but these are super big dots, okay, on this map. So the CO2, the original sighting of this at Point Barrow, at Mauna Loa, at Samoa, and at the South Pole were chosen in remote marine places because the land is such a mess, okay? Creates the CO2, the vegetation gives you a cycle that is about 50 parts per million diurnally, maybe seasonally. And what we saw in Mauna Loa, top to bottom, is 6. Okay, and you try the trend is about 1 ppm, now it's about 4 ppm per year. Right, so you don't want to be somewhere where it's going 50 parts per million and wet seasons and sunny days, and okay, so the noise, to get that signal out of the noise is impossible. So the original sites are way out in the remote places. And so from the sites, we can now make a flying carpet of CO2. Okay, so here is the North Pole to the South Pole. And so this is time going this way. So you can see what we saw at Mauna Loa here, that obviously it's increasing, the CO2 is increasing at all the stations. The seasonal cycle is much larger in the northern hemisphere at high latitude. And that is because the growing season is telescoped, okay? And so the asynchrony between the photosynthesis and the decomposition is much greater. Whereas in the tropics, they not exactly, but they sort of at the same time. So even though there's a lot going in, there's also a lot coming out at approximately the same time, so the seasonal cycles are very small. In the southern hemisphere, where there's little land, less land, and less vegetation, then we're dominated by the ocean, and the cycle is about 6 months out of phase with that in the northern hemisphere. So what you note here is that the northern hemisphere has higher concentration than the southern hemisphere. And that is because the mixing time is in the tropics, the clouds go up, the intertropical convergence zone goes up. Okay, the Hadley cell does that. And so for the CO2 to cross that barrier, it takes about 1 year. Okay, so you can see it takes about 2 to 3 months, and cross the equator takes about a year. So I just said that. So now what I want to show you is the fossil fuel. Why is CO2 increasing? Now nothing is working. I need help. Oh, this is unusual. When we tested it, everything was working. I can't. There's a movie sitting in here that shows you where the fossil fuel CO2 is, where the fossil fuel CO2, how it has changed in time. So what I did a long time ago is I actually hand digitized the world map and hand added cities and so then what we did was map the emission by country or by county or by whatever onto the map. Can we do it? It worked when we were testing it. I'll show it. No. Ooh, well, I'll show you later. I'll show you. I'm sorry, when we tested everything. So what we have, and we'll go through this. So you get the sense that the emissions started in Europe. Okay, and then spread to the US and then spread to other parts of the world. And so at the end, you'll see where the emissions are. And I'll show you the movie later. So here is the emission integrated over all the area. Now this is missing. What happened between the testing and now? Anyway, so you can see the 1990s to the present, so the growth rate of the emission from fossil fuel combustion. Okay, so we're now at 2.5, increasing at 2.5%. This looks small. This looks smaller, but we're multiplying a smaller emission. So now we're going fast, growing very fast. We thought this was the utter limit, but it's faster than what we have been doing. So I think you all are familiar with this. So let's go to deforestation. So the big trees and things going on, and so again, the deforestation is a source of CO2 because we've reduced photosynthesis, but if the layer is there, there's enhanced decomposition. And there could be immediate release of CO2 because of fires there. So if I look at Rondonia, which is the poster child for deforestation, this is 2000, 2001, 2002, 3, 4, 5, 6, etc. So you can see the rapid growth of roads, okay, and so the building of the highway and the growth of the development along the highway. But this is not the full picture, because if we look at the whole of the Amazon, then this is, and by size of deforested areas, what you see is less than 1 hectare, okay, 100 hectare, 1,000 hectare. Then you can see the large clear cutting in the Amazon because of large corporations owning the land, or if I'm a very wealthy landowner, the way I tell people, don't settle on my land is by clearing. Okay, so then you know you can't do that, it's my land. So there's a lot of, so there are lots of reasons, it's not just a highway, but this is a dramatic picture of the rapid deforestation. Okay, so when we put the whole thing together, here's the fossil fuel release from 1960 onwards. And here is the land use change. So this is a smaller, this is a peak fire in Indonesia. And so there's a little bump here. So you can see most of the CO2 is from fossil fuel, less so from land use change. And so let me just stop for a second and ask, well, how do we know CO2 increases due to fossil fuel? We see the fossil fuel and we see the CO2, okay? And then where this, so this is one piece of evidence. Here is the CO2 again in blue, okay? And the C13 is going down as the CO2 is going up. Okay, that means that the biology, okay, the fossil fuel is old biology. Okay, the deforestation is new biology. And with the biology photosynthesis, the light guy, the CO2 goes in, and the C13, more C13 is left in the atmosphere. So the C13 is opposite the CO2. And so you can see this decrease. The decrease means we're adding biologic CO2 to the atmosphere. And the other is the C14 is decreasing. Okay, the ratio of C14 to C12 is decreasing. Remember, the fossil fuel is very old carbon, and the half-life of C14, okay, 6,000, I just lost all the digits, over 6,500 years, okay? So there's no C14 in the old carbon. Okay, so this is one clue that the CO2 in the atmosphere is from the addition of old carbon, okay, that's of biologic origin, and some new carbon in there as well. But also what we see, and this is a very dramatic thing, and we now have it as CO2 is going up, oxygen is going down. Okay, this is the guy who went up to Mauna Loa is Dave Keeling. The oxygen is made by his son Ralph Keeling, also at Scripps. And you don't have to worry about running out of breath. This is in units of per million. This is in per million, and this is part per million. So this is the oxygen to the O2 to N2 ratio. Okay, so this is very clear that this is combustion cycle. Okay, when we burn the carbon, we use up oxygen. So the other piece of information here is that when we look at Mauna Loa versus the South Pole, you see what I showed you on the flying carpet. Mauna Loa is always higher than the South Pole. And you can see South Pole tracking Mauna Loa. And if I plot the difference between Mauna Loa and South Pole versus the fossil fuel emission, 96% of the fossil fuel emission is in the northern hemisphere. 96%. Okay, so the CO2, if I start like this, the CO2 in the northern hemisphere, CO2 goes up. It takes a year or so, the CO2, the southern hemisphere follows. Okay, and you can see it very clearly in the record of the difference between Mauna Loa and the South Pole. Okay, so this is for me, it's like it's biologic. It's the CO2 is increasing because of the combustion of fossil fuel, mainly. Okay. So then where does it go? Oops. So when we look and convert to the same units, then here is the Mauna Loa record, but not this concentration, but the derivative, the year-to-year increase in the concentration. And here is the total emission of fossil fuel plus the deforestation, the land use change emission here. So what we find is that approximately half the atmosphere, the accumulation in the atmosphere is about half of what we put into the atmosphere. Half of it has gone into the land and the oceans. Okay, and you can see here some years the land and ocean take up very little. A lot of it is in the atmosphere. Those are warm, those are El Nino years, and some years more go in. Okay, and so this is what we're seeing: the changes in the ocean circulation, changes in the climate, changes in the biology. And I know when there's no water, my plants don't do very well. They don't take up, the large tracts, the forests don't take up as much carbon. So, put another way, we put CO2 into the atmosphere. Fossil fuel is about 90%, deforestation is about 10%, about half, this varies from year to year, it's about half in the atmosphere, a quarter in the land, and a quarter in the ocean. Okay, so this is a budget calculation. And so, so this is the land part. It's most difficult. You can see it's calculated as the residual of all the flux components. Okay, so for the ocean, we can go out and measure, and because the currents move CO2 around, we have a few ships, okay, not a few ships, quite a few ships, we can go and measure the CO2 that has gone into the ocean. For land, it is like collecting stamps. Okay, so this is very difficult where the CO2 has gone in. We can say from the atmosphere's point of view, but from the ecologist's point of view, this is a really challenging problem. So the CO2 that has gone into the ocean, so this is Mauna Loa, and near Mauna Loa there's an ocean observatory. So the CO2 is also increasing in the ocean water. And so you can see the pH at Mauna Loa by Hawaii, okay, in the water. So the ocean has become more acidic. Okay, this is a concern. You hear about ocean acidification. I worry about the ocean. First is the acidification of the ocean. The chemistry will say more of the species in CO2 and more will come up. Okay, but there are other biological consequences of this. So another thing is how fast will CO2 increase. So here you can see there's a drought, so the drought, there's less photosynthesis and the CO2 is higher in the atmosphere. When we have return of the rains, okay, there's more photosynthesis, etc. Why am I talking about this? Climate is changing, right? We're now counting on the land and ocean to take up half the fossil fuel, all the anthropogenic CO2. So when the climate changes, what would happen, okay? The land and the ocean, will they take up more carbon or will they take up less carbon? How fast will the CO2 increase in the atmosphere? Depend on, not just on our energy consumption and what we do, but also how the land and ocean help us remove some of the CO2. So the outlook, from my calculation of the last century, I put in the interactive carbon, I grew leaves in the climate model every 20 minutes, and I did all the chemistry and all the biology in the ocean. And at the end of the day, the observation is the decreasing land and ocean carbon sink, but at the end of the day, we're suggesting that the warming will feed the warming because the capacity of the land and ocean to take up CO2. Right now we're thinking 50%. Okay, that 50% will decrease as we warm because of changes in the biology on land and changes in the ocean circulation. The ocean will become more stably stratified because we're heating from the top. Okay, so it's tougher to move things out of the way of the atmosphere. Okay, to hide it from the atmosphere, etc. Solubility changes, the acidification, etc. So all of that means that the fossil fuel emission will go up fast. Okay? So now we go to the climate treaty. So the United Nations Framework Convention on Climate Change, 1992, the objective is to stabilize greenhouse gas concentration and mainly CO2 in the atmosphere that would prevent dangerous anthropogenic interference with the climate system. Okay, so there's a lot of discussion since then. What is dangerous? Okay, I won't go into that conversation. But the level should be achieved within a time frame to allow ecosystems to adapt naturally to climate change, to ensure food production is not threatened, and to enable economic development to proceed in a sustainable manner. So that's an aspiration. Okay, very nice aspiration. So then, in addition to the Intergovernmental Panel for Climate Change, which is scientists reporting on what we have learned, there's also the COP, the Conference of Parties, which is participation by government officials to say what we will agree to and what we want to agree to. And so what they did was emission targets and Kyoto, which has now expired December 1997, that they aim for 5% below 1990 levels over the 5-year period. Forget it. We did it. No, nothing. Okay, we're growing fast. The emission has grown faster than anything that we thought was possible back then. So what we come to here is treaty verification. One of the thinking that is that we cannot agree to treaty to do anything, because how do I know if I did it that you didn't do it, okay? So if I do something, so how do I know, and how do we know, we were in this committee where before the Copenhagen meeting was, how well do we need to know? How well can you measure? You know, if we reduce emission by 10%, can you tell? Okay. Or at what level can you tell? And all of those things we haven't done anything about. So here we're talking about treaty verification. How do you do it? So the United Nations has basically the greenhouse gases they will consider, and here is fossil fuel. It's from CO2 is the major player here. There's other CO2 from deforestation, methane, nitrous oxide, etc. Other greenhouse gases, and I'm going to say freon, trademark freon, the CFCs and the replacements here. So I'm going to focus on CO2 here. So the method right now, I showed you fossil fuel emission. Okay? Okay, we know it very well, and here's the C13 and the C14. But what we have is based on socioeconomic statistics. It's self-reported data. Okay, so the US, I will go through, we have the Department of Energy and EPA. Okay, I'll show you this. I'll go back to the US, but some countries don't know how to report. Some countries, I won't name, it's none of your business. Okay, some countries do not have the capability to survey the entire country, to survey the CO2 emission, the fossil fuel consumption in the country, and so then there is always update, etc. But some countries will say, you know, some smaller countries, and they won't impact the budget because some smaller countries don't know how to fill in the. The United Nations sends out a form that says, please fill out this form, okay? And the way, and even now in California with the cap and trade, it's like, please fill out this form, okay? And so, and there's a spreadsheet and how much of this, and then what they do is the Department of Energy in the US, very good record keeping. The DOE has an inventory of fuels, you know, coal, and the quality of the coal, the energy content of the coal, and you convert the energy content into CO2 emission if it is complete combustion, okay, and where the oil and the import, etc. So we have good information about the fuel. EPA is the inventory of the consumption. So you have some emission is some activity like steel production, and so some emission factor, a lot of work is done on the emission factor. What, for example, what is the emission per ton of steel produced? Okay, so it's a lot of spreadsheet, it's multiplication, it's pretty good, okay, for the US, the big emitter. So here is the coal train, a mile. If you read John McPhee's marvelous book of the coal train, how the guy at the front controls the uphill and downhill, you know, how the different carts. But anyway, so this is for the Department of Energy, they have the mass of fuel, and because the coal is crushed into very fine particles, it's complete combustion. So if you know the quality, then you can estimate. And EPA at several places have direct measurement of the stacks, and so in the US, when we have very good numbers, we agree to 3%. Okay, so we don't know about other countries, how they do it, what quality of coal, it's just a spreadsheet that they use. So what we want to do is trust but verify. We're not saying anybody. So where I come in is to use a top-down, the atmospheric scientist point of view. If I have a CO2 sampler here, and we have land, and we have emission, then the concentration will increase downwind. Okay? So if I could measure the CO2 in the atmosphere, if I knew which way the wind was blowing, I could figure out what was going on, what came through here. So So the method, what I just said, is the bottom up is what I just talked about, the statistics, the spreadsheet, the multiplication. But what we want to do is to do top down. So we have climate models, we have weather forecast models. So you can do a tracer, we can emit, we can in the model different amounts of CO2. Okay, so 1 gigaton, so those of CO2 from North America, for example, what the signature would be. 1 gigaton from Asia or Australia. So you do a lot of these calculations when you go through. And so at the end, you do a Bayesian or a combination to say, given the observations that I see, the flight carpet, okay, the north-south difference, the seasonal cycle, can I find how much actually came from each region? Okay, so then that's the backwards, the inverse problem. So then we, for large regions, estimate what the natural and sources and sinks. And so I really need to know the wind, and I need to know the convection, I need to know what is the weather, etc., so that I could do this calculation. So what we want to do, but even so, the CO2 data, as I mentioned, is in the remote marine locations, and we want to know what is happening on the continents, and we're not measuring CO2 on the continents. So what we want to do is to deploy a CO2 sensing satellite, and so new and other things, we are actually having new atmospheric sampling stations. I won't have time to talk about where we have little sensors in a little box, $4,000 a box, which we have put in schools in Auckland. And so there we have 40 of these. And so you can tell which school the parents come at 7 or so, and I know the car and see it goes up. And which schools don't have that, and etc. So you can see summer when school is out, etc. We also are testing a new thing, which is in cars. So you can drive around and see who is the emitter, and etc. 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 So there are other things that we're doing, but that's very local. Okay, so I need something which is global to go where we won't go. Okay, so here comes the orbiting carbon observatory. I like this. Somebody said, "How did you pick that name?" I said, "Aren't you nerdy enough? Don't you recognize this guy?" Okay, this is OCO. This is the CO2, the molecular structure of CO2 right here. Okay, so what is really cool about this is it's really high resolution. We use the weak and strong CO2 absorption band, 1.61 and 2.06 micron. Okay, so this is sunlight. Okay, so you know at this hour how much sun comes in and it is absorbed. So you know how many molecules of CO2 per centimeter squared are in your path. Okay, but sometimes you look this way, sometimes you look that way. So you need to know your path length. So you also measure oxygen. Okay, so what it senses, a sensitive instrument is sensitive mostly to CO2 near the surface where the action is. So it's cool because the footprint is 3 square kilometers. So every time it takes data, there are 8 of these. Okay, each one is about 3 square kilometers. And the data rate is 3 hertz, so 3 of these. So we take 24, okay, in 1 second. And the satellite's going at 7 kilometers per second. Okay, so in 1 second, in an area which is about 10 kilometers by 7 kilometers, if it's clear sky, we will have 24 observations. Okay, if there's cloud, we make it small so that if the cloud, maybe we can see through some of the clouds. Okay, so this is really exciting. And so the repeat cycle, it will come overhead about 1:15 in the afternoon. At Equatorial overpass time is 1:15 in the afternoon, a 16-day repeat cycle. Unfortunately, I still can't talk about this. It crashed, and we launched 2009. It went into the ocean, it went into the Southern Ocean. So for me, it's difficult for me, because I did all the work. I started working on this in 1980. The first meeting I went to was 1981. one. Been building the models, looking at this, and doing the other observations, and writing the proposal. I'm not the PI of this, I'm not an instrument person, but being part of the proposal. So what happened after that was that I went on more committees, more working trips, more report writing, but basically we argued for reflight. And the argument is not the science. The first round we argued we don't understand the carbon cycle, we need to understand where the CO2 is going. So the second round, because all our friends will say, you have your turn, it's my turn to fly. Okay, so this was actually supported by the State Department and the CIA. Okay, so we got approval for reflight, and so it was this summer. And so on July 1, it was supposed to go, and it was aborted. You go midnight, you get on the bus, and you go out to Vandenberg Air Force Base. It's cold and by the foggy, and you go into this parking lot, and there are food trucks and large TV screens, and you stand there and you do the countdown. There are 2 countdowns. The first countdown is just all the instruments, and then there's a break, and then there's a second countdown. The launch window is 30 seconds because we have to go to a particular spot. So T minus 42 seconds, there was a hesitation. You go, it's system something ready for launch, system something ready for launch, and then nothing. Okay, so that was it. Okay, so we were lucky the next day, and I hope this works, that I can show you. Because it was, so the next day we had a science team meeting, and so...
Green board, T minus 10,
and so,
9, 8, 7, 6, 5, 4, 3,
I can't tell you
2,
what the
engine
nervous
start.
wreck we all
So
anyway.
the Delta II rocket with OC.
But the first one went this way also. And they cannot separate the instrument from the rocket until it's over, it's past all the people of California, Southern California, and it's out in the ocean. This is what the guys are seeing in the control. And so this is what we want. I'll stop right here. So it's actually blown out. So I'll stop this.
The new dev coming up on
Go
1
back.
line.
Come back here. So it's launched. So we're very excited that it launched, and so the OCO, so OCO has to go at the front. This is the series of satellites called the A train. Okay, so OCO is now at the front of the A train. So the equatorial overpass time is 1:15 in the afternoon, and the last guy is about 20-some minutes later. Okay, so this is a whole series of satellites that will measure aerosols and sea surface temperature, water vapor, clouds, center temperature, pressure, and clouds and aerosols, and other things. Okay, so when the satellite got launched, it went into some parking space up there, not at the front of the A train. So then they could test all the communication and all the systems are working, and then slowly move it into space. And it took, I'm going to say, I forget, like 2 weeks, because the instruments were at ground temperature, and so to cool it down to the temperature up at 705 kilometers, it takes a long time. And so you really can't calibrate the instrument until it has cooled down to the right temperature, etc. So we're still finding our fingernails. The first data expected shortly. So we'll see what they would show. Okay, so what I want to finish here is that the OCO data, so after the data, so the satellite is going, it's like wrapping yarn, okay? So it's like a noodle of data that comes in. So what we're doing then is to use the model again, pull in the raw weather data and the CO2 data at the same time, so do this data simulation, mashing everything together. So into a global climate model, and most of you are using a carbon filter. So then, once I know how the winds are blowing, what the CO2 concentration changes are, then I can figure out what was at the bottom. okay, what gave it the concentration that it has. So this is the goal is to infer the surface fluxes from what we measured in the column and from the winds and the transfer. Okay. So the summary for climate treaty verification is that we need to verify self-reported emission estimates. And with the satellite data and with the climate model, with the model data, what we hope to do is to get things at the sub-national level, at every model grid box, so that you're not saying, oh, this country versus that country, I'm going to look at spot by spot. And the nice thing about this, the important thing about this, is that the NASA data are available to the whole world, free, once it's processed. And our models and our machinery, once we test it, will be out there also. So what we've done in the past, when all of that is out there, then every country can have a running start. Okay, so then they will do their own modifications of what we've got. Okay, so then we can have the same data set, we can have the same thing, okay, same machinery, same data, and so to figure out what the emissions are. So I'm not counting on the self-reported data that are for a large part of the world not very accurate. So I'll end here. What I want to end here with is that in this spring this is the climate series. So in February, we released a report. The Royal Society and the National Academy of Sciences released a new report. I was the US lead for this report. It's only 40 pages. I wave it in front of all my friends. It's only 40 pages. Okay. So what we did was the climate basics, but we did 20 questions that you can see here. Okay, so it's written very plainly. We have a short answer, and if the microphone is in front of your face, okay, here is the short answer, and there's a longer answer with the graphics, and we don't talk about, I work on climate models, but here we're arguing, here is the evidence. So the title, the small brochure is Climate Change Evidence and Causes. Okay, so we can go through if you want to ask me questions about that report, about the recent hiatus in the warming, or whether the sun is important. We have we have done all of that. So I'm happy to answer questions about that. So I'll stop here, and I thank you very much for having me here.
We have time for some questions before we go and have some food. Yes. Go ahead.
Thanks for the very enjoyable talk. I wonder if you had any reactions from other countries to the U.S. having this capability, and certainly it'll be shared with the world, but that's also a U.S. capability to observe CO2.
I think as long as the data are out there, Japan has a satellite called GOSAT, and that is of the same vintage. They launched, ours crashed in February, they launched in January, and theirs is working. We have a 3 square kilometer pixel. They have a much bigger pixel. They don't have, we have all the grounds, but we have quite a few ground stations looking up when the satellite's looking down. So we have calibration that's tied, not just the ground stations looking up when the satellite's looking down, but that's also tied, this is a very cool thing, called a new air core that you can, like with a balloon, it would get the air, like an ice core, so you can get the vertical profile of CO2, and that is also referenced to the flats, the lower record, so that you can actually do the comparison. The GOSAT got launched, but it's still working together to help them do the calibration. So there may be European satellites, but I think that in the satellite realm, because the data are shared, you can do anything you want. Okay, so I'm thinking about climate treaty verification. I'm trying to figure out where on land the CO2 has gone. Okay, this has been my thing for a long time. I'm going to say 25 years ago, I wrote a paper that says that because of the north-south hemisphere, the gradient, I said if all the CO2 were in the atmosphere, or all the fossil fuel CO2 were in the atmosphere, I'd get a gradient that big, but the observed gradient is smaller than that. So that means the CO2 has to have gone into the northern hemisphere, and because I know this ocean measurements, I know who took the ocean measurements, it has to go into the land. The oceanographer says, no, it has to go into the Southern Ocean. I said, no way, because if it's gone into the Southern Ocean, we would have exaggerated the gradient. So we're still having that argument. Okay, has it gone into the land? Has it gone 25 years? I think I'm right, but I want some data. I want some data. Okay, to say I'm right. Exactly, so we're getting, so the answer is that because the data are available as CO2, not as fluxes, okay? The CO2 measurement is a clean measurement, okay? So you can do whatever you want with it. And we offer, if our modeling is successful, we offer that as well, that you don't have to use it. Okay, does that answer your question?
Questions?
You can ask me about the climate as well.
Yes, I'm sure I think you were talking about this in part in your last response, but I'm wondering how you estimate the uncertainty and how good you think you can do with this method of estimating emissions.
We don't know yet. I'll just go back to weather forecasting for a second. If we make an ensemble. I'm a beginner in this, so I'm poor. So I only run 64 of the climate model and make forecasts. The weather guys have like 100 and it's super high resolution. But you can imagine if you plot something, pressure, 500 millibar height of the 100 ensemble. If no weather is going on, they look like raw spaghetti. Okay, they all go together. But if there's going to be a storm, they look like cooked spaghetti. Okay, because of a lot of possibilities that could happen. So a lot of it, there's the CO2, the satellite observation, but also the weather uncertainty. Okay, so we are struggling to say how much, because I need the winds, etc. We haven't done it yet, and I hope when the data comes in, I can answer that question. But we have done a lot of OSSIs, the simulations for this, and the CO2, I think, just filling in. The first step is filling in, okay, because it's this noodle. I need a map of the whole world. We think we can do it 1 to 2 parts per million, but what we're struggling with is the bias, and that's something we don't know how to do. We don't know if there's a bias, and we don't know how to do it. So there's a lot of work going on at the moment.
Other questions?
I was just curious, just with OPO2, you actually measure, every side on the planet, and if so, for a given side, how often do you actually take that measure?
Say that again?
Well, so I was wondering, do you actually cover the entire planet with
Yes.
OPO2? Do you really monitor every side on Earth?
Yes.
And how often do you get a measurement for each side?
How often?
Yeah, is it like daily or weekly or?
What?
So just for a specific location.
For the satellite. Yeah, the repeat, my little 3 square kilometer. My little 3 square kilometer is every 16 days. That's the orbit. Okay. But if you think not my little 3 square kilometer, but let's go to a larger region like 100 or 1 degree by 1 degree, then I will have a lot more observations within that period. So because it's a sun instrument, we don't get the nighttime. And so there's another instrument on the A train that uses the entire thermal spectrum, so you get CO2, vapor, and methane, and everything else. There, it doesn't day and night, but it gets the CO2 halfway up, not near the surface. So we're combining all these instruments together. So the OCO is the sharpest eyes in the sky, because the AIRS is about 100 square kilometers and halfway up. So we try to combine everything together to do that. I'll see if I can find. Other questions while I find them? You can ask me about climate. We just did this whole report.
Yeah.
Right?
The wind data seems really critical to
Yep.
your calculations. And so clearly you have very good records of the winds in some cases and not necessarily in others. How well constrained will winds be in some of the parts of the world that might be the greatest interest?
Well, that's where the physics comes in. Okay, so so we're using the physics to interpolate, if you will, and the consistency between the wind and temperature gradient, because you can have the physics that would constrain all of those. So it's not just puffs of wind here and there. So that's why you use the entire weather forecast model. Okay, and so you do that in the simulation where they filter out what the puffs
It's
are.
mostly coming from the model.
Hmm?
It's mostly coming from the model.
The data filters through the models, okay, or using the model to extract it. One of the goals, and we don't know whether it works or not, is that in the Southern Ocean, South Pacific, there are very few wind observations. So then we're hoping that if we have CO2 observation, then we could improve the wind information there. Okay, so it goes both ways, but we have to demonstrate it. I think can you turn down the lights a little bit? So you can, so you can see the emission here, starting here, going to spreading. I can start again, but you get the idea. Starting to Japan, in North America, and South Africa. So this is a mapping. It's not a real thing. It's just mapping of the socioeconomic statistics. So you can see now where the emissions are. Okay, but it started here, and so this is what makes the negotiation so difficult. Okay, whether you do this year or the last 5 years, who is the biggest emitter, or who is the biggest emitter through the history of emission, or do you do it by per capita? Obviously, China has now a large emission, but the per capita is much lower, etc. So the whole challenge of the negotiation is how do you deal with the different views of emission, and how do you do the negotiation, and how do you balance them?
Play it again, please.
I'm glad this worked.
Is this available online?
Yeah, it's. Oops, what did I do? No.
Just going back.
How do I make it? Here, push the. challenge with the negotiations is that we are a global economy. So the U.S. has out, if you will, the large industries have gone overseas, and so in a sense, we've outsourced our CO2 emissions to other parts of the world. And so we import goods, and then we don't count that. We don't count that, the production, CO2 cost of the production. So, you know, I'm in California, we want to eat local, but then when I look at the orange juice from Florida, the CO2, I just blanked out on the number, but it's the fertilizer application, not the transport. Okay, for the gallon of CO2, for the gallon of orange juice, the CO2 cost is in the fertilizer, the production of fertilizer for the orange groves, not the transport from Florida. So there's a lot of stuff is how we think about the CO2 emissions and what we do to reduce the emission. So at the end of the day, we think about four steps. One, you know, in the climate and the CO2 space. The first one is energy efficiency, and you know, so all the in California is always the refrigerator. You can see ever since Art Rosenfeld came up with and his group came up with the Energy Star. Okay, so then you can see the California. Okay, so the consumption, energy consumption per refrigerator has gone down. Okay, but now the manufacturers have made bigger refrigerators. So what is limiting that is the size of your door. So unless you build a new house, you can't have a big refrigerator. Okay, if you renovate a house, there's a limit to how big your refrigerator can be. Okay, and so now the manufacturers are doing doors and other ways to get more refrigerator. Okay, but there are lots of, so the first step is energy efficiency. A lot of companies, you know, all the things I plug in, a lot of are improving the energy efficiency. The second thing is alternative energy. So a lot of research going on, but it's not yet scalable to replace what we've got. The third, in the climate space, we think about is carbon capture and sequestration, how to suck CO2 out of the air and hide it somewhere else. With Norway, Statoil has done that very successfully, and they put it because they extract the oil, and so they can put the CO2. So CO2 is heavier, so actually we push the oil up, and so it's much easier. It's called enhanced oil recovery. Okay, so it's easier to get the oil and the CO2 than fills up the space. Okay, but it's tough when you have tons of saline aquifers, but to put the CO2 in the aquifers, you have to make sure that there's a ceiling, because CO2 would be acidic. Okay, so it could leach out the arsenic and the mercury and other stuff that could enter into the water supply. So there's a lot of seismic stuff to say where we can hide the CO2. And so that's the third thing, is carbon capture and sequestration. And the last resort is geoengineering, where you put aerosols and stuff and reflect more sunlight and do other things. Okay, so we think about, but I think the easiest thing for the carbon, for the CO2 and climate problem, is to reduce wastage. Absolutely reduce wastage of energy. And a lot of the manufacturers, all the electronics guys are totally onto this. So that's a good news. Okay?
Another question?
Nobody wants to talk about the hiatus anymore?
Okay, tell us about it.
Huh?
Tell us about the hiatus.
You know, the temperature has been increasing since has been increasing. And then 1998 was the big El Nino year. And then the temperature has sort of fluctuated around there, hasn't gone up much. And so you read the press as, global warming is not increasing at all. And so Thomas Stocker would say, here's the CO2, and you're sort of worried about stuff up there. Okay, if you look at the decade of the last, if you look at the warmest 20 years since 1880 when we have good records. 18 of those 20 are in the last 20 years. Okay, so my freshmen obviously have lived in the warmest part of that long record, and they're living in a climate that's warmer than their parents and warmer than their grandparents' climate. But if you look at that, if you do the accounting for the energy, the atmosphere has very little mass, okay? 90% of the energy has gone into the ocean. So we have very good record of the ocean heat increase. So during an El Nino year, we have warm sea surface temperature, and the ocean is heating the atmosphere. During a La Nina year, it is cooler sea surface temperature. So number one, it's easier. The stratification is such that it's easier. You have cold water on top of warm water, so it's easier to mix things down. So we've been in this La Nina. I'm in the drought forever. So there's more heat in the ocean and less in the atmosphere. So basically, you have 90%, which is 88 or 92. Okay, it does that. So it's very clear, something that we expect, that this natural variability, that some years will be warmer, some years will be colder. We just are in a long-ish La Nina, so more heat. And now we have the Argo floats. They go roaming, they're autonomous, they roam, and they go up and down, and they take temperature and salinity. And we've got, I think, 3,000 of them. And so then we now have very good measurements of the temperature structure, so we know where the heat is coming. Okay? So we're very sure, the energy has gone into melt. Some of it has gone into warming the atmosphere, obviously, but melting the ice and going into the ocean. So we can account for that very well. That the hiatus is just because we're in a La Nina state.
So what if we continue this discussion over food?